We're going to end our reaction postulations unit with a different, kind of crazy way to think about a type of reaction from last year. Before we do that, though, before I introduce you to half reactions, I want a tangent for a moment. You people at home, make sure that you have your slides out. The tangent is on the opening slides. I want to revisit particulates for a moment with you. And bring particulate diagrams into the reaction. I can't get to it easily. Into the reaction postulations that we've been talking about and let them marry up a little bit. So I don't think you'll have any trouble with this first part. But let's draw some beakers together. In the first beaker, I'm going to put just water. Now, we're going to draw this liquid water together. But for the most part, College Board doesn't make y'all draw water. Whenever there's particulates that involve solutions, most of the time they say omit water molecules because they want you to focus on all the other chemistry. But I wouldn't be doing my job if we didn't draw liquid water. Just under the assumption that anytime you make a solution, you're usually putting solutes in water. So what does liquid water look like for a particulate? Somebody kind of describe it. All right, big circle and two little circles. That's perfect. Mickey Mouse. All right, but since it's liquid, what should be true? That would be gas. Yeah, at the bottom, but disorganized, right? I don't want to make it super organized, or that would kind of indicate that it's ice. All right, so you can see that I've just got water along the bottom, but disorganized. Big circle and two little ones to represent the two H's and the O. But again, I don't think you're going to have to draw a lot of water in this regard, at least. Let's draw up another beaker. In my next beaker, we're going to add solid potassium iodide. Solid potassium iodide. Now, we're kind of adding this solid potassium iodide into water. That's what we're going to be imagining. So we're dumping it into this one, but I'm not going to draw the water molecules again. Hey, what is true about the solubility of potassium iodide? Does it dissociate? That was an unimpressive response from the class. I'm glad you couldn't see that at home. It does. You know why it does? Because Big Daddy says so. Big Daddy rule number 1 says if you have an alkali bonded, it does dissociate. Rule number 2 also says it dissociates, the halogens, because potassium's not an exception. So it's going to dissociate. So let's make this float around dissociated. Of course, when they dissociate, they gain their normal charge. All right, they're electrolytic. And look at my ratio. I did 2 of each. I could have done 3 of each. I could have done 4 of each. Why could I not have done 2 of one and 1 of the other? Because the nomenclature is a 1-to-1 ratio. So make sure that your ratios, when you're drawing particulates, always make sense. Let's do another beaker. In this beaker, I'm going to dump in lead 2 nitrate. Solid lead 2 nitrate. Now, this is a totally new beaker, but it contains water already, so we're dumping it ultimately into one of those type of beakers. Hey, what is true about the solubility of lead 2 nitrate? Will it dissociate? Yes. Why? What rule number says it will? 3. Now, again, you don't have to know those solubility rules by their number. It's just a good way for us to talk. But yeah, Big Daddy number 3 says nitrates are always soluble. So dissociate them. Oh, here I did not write this. It's lead 2 nitrate. Oh, it's just written like that. Anyway, so yeah, let's dissociate and make sure they have their proper charge. Hey, if I drew 2 of the lead ions, how many nitrate ions should I draw ratio-wise? 4. Look. Y'all, look. It's really easy. There's only 1 lead and there's 2 nitrates. So if there's 2 leads, there needs to be 4 nitrates. Now, I'm not saying that you had to draw it like this, all right? And I don't care where you put these floating pieces because they're floating just crazily throughout the solution, but the ratio must be correct. All right, so if I only did 1 lead, I would just do 2 nitrates. But since I decided, because I'm crazy, to do 2 leads, there has to be 4 nitrates, because there's always twice as many nitrates as leads based on the form. I want to dump those 2 beakers together now. What would happen if I dumped this beaker into that beaker? Well, that's where our good reaction postulations will show up. All right, so if we mix them, what will happen? Well, here's what you need to think about. We are ultimately mixing Ki with PbNO3 too. So we need to consider what the products are when you mix them together. So, like we've been doing, let's do the ion swap, the first part of each, which will make lead iodide. All right, it's lead 2 iodide if you look at the reactant. And the potassium nitrate. You're always welcome to stop me if you don't know why something happened. Balance. All right, 2 iodines. So 2 iodines, 2 potassiums, 2 potassiums. That'll fix it. But why did I do all that? Because I want to know what's this if you mix these together. And it's the products, right? That's what forms. When you mix them together, it forms the products. But the solubilities of particulates will be really important. What is the solubility of PbI2? Well, I heard it what? Insoluble. It is a solid because of rule number 2. Iodine is usually aqueous, but not if it's bonded to lead 2. What's the solubility of the other product? Yeah, aqueous because all nitrates are aqueous. And now I've got the info I need to draw my particulate. Where should the PbI2 go? Yeah, at the bottom, because it's a solid, right? So my PbI2 would be hanging out down here. All right, now I'm kind of shorthanding that. Sometimes they'll let you. What I mean is they might have given me a legend with shapes. Remember, we did that before, where we would have to show the shapes touching each other because it's a compound. But since it's a solid, that's where the particulate would go. What would be true about the KNO3? How would I show it? As ions still. If it's aqueous, it is still dissociated. So they should still be floating around. But again, watch your ratio and just make it make sense. Do you see how I drew two PBI2s? But a click of the reaction only produces one PBI2? So if I drew two of these, that means the reaction clicked twice, which would make four of those, which is why there's four Ks and four NO3s. There's a lot to think about. Well, yeah, because it's aqueous. Exactly. This is kind of a joining of different things we've talked about together to make College Board impressed. But now my ratios are good, a 1-to-2 ratio of the products. The solid is solid, the aqueous is dissociated, and you can really see the spectator ions now. What do I mean by that? Well, look at the starting beakers. Do you see how the K plus and the NO3 minus was floating around before you mixed them? And they're still floating around after you mixed them? It's because they didn't do anything. They spectated. But do you see how the I minuses and the PB plus 2s are gone? They did something. Non-spectators. They would be a part of the net ion. Just a joining of stuff we've already talked about. Are there any questions? Yeah. Did you the two at the bottom, or is that just like? Yes, because it's solid. So particulate-wise, that state of matter will be at the bottom. There didn't have to be two of them. You're right. I could have only drawn one, in which case there would be half as many of those up there. Right. So I like to show the number that doesn't match this so you can see that I'm just matching the ratio no matter what. Now, there's one more beaker that your notes had you draw. And you won't have to draw what I'm about to draw in this class, but I just want you to see that you need to keep this idea separate in your brain. It says, what if you added sugar to the water? All right, I'm just going to use glucose, but it doesn't matter what sugar you pick. But if you add solid sugar, will it dissociate? What's the answer? The answer is no. It won't, because electrolytes dissociate. Non-electrolytes don't. Y'all, that is a non-metal covalent. Covalents are non-electrolytes. Therefore, this doesn't apply to covalent compounds. It's very, very important. They are not electrolytic. No pluses and minuses. You know what it does? It just saturates, is what we say. But like I said, you're not going to have to draw this. But it does go into solution, but they all stay bonded together. They just become saturated by sugar. Whoa, that's a big 6. Is that the formula? It's formula for glucose. Your table sugar is C12H22O13. Sucrose. Anyway, you don't need to know that either. But anyway, I just want to point out that all of this stuff we're doing with dissociation is only for electrolytes, acids, bases, and soluble salts. Everything else does this. Similar to that. It'll get wet, but it won't pull apart. Yes, you'll need to know the idea behind this for sure, but I don't see them make you draw covalent compounds out of it. But they might have to. Absolutely. Justification on why it's not electrolytic and stuff like that. Are we good? That was my tangent. Do you want to do the lecture now? I mean, it was part of your notes, but that's not my focus. This was not my. You just needed to see it. Okay. Look here. Half reactions are not fun. There's a chance that your opinion when I'm done with what we're about to do will be the hardest chemistry thing that you've done so far in your career. But I don't want you to think that we just do this. That, it gets harder and harder and harder. No, we do a lot of this, a whole bunch of this during the year, which means if a topic gives you a bunch of trouble, there's a really good chance that the next topic is going to be your cup of tea. So don't think that we're always just climbing to harder stuff. But half reactions isn't fun. There's so much room to get confused. And the steps to do it are long. All right, you already wrote them down. I think. And it's not a lot of fun. It's a type of reaction thought that you've never had to do. So Be patient with yourself. Realize your exam is 8 calendars away from me finishing this. You have a ton of time to get good at it. Are you ready? Okay, so one of the types of reactions that we covered last year was single replacement, but we had a nickname for it. We called it a redox reaction. You might remember that we did this thing where we would track charges from one site to the other, and we could pick what species was oxidized and what species was reduced. That vocab is up there, and that's important. I do want you to know that vocab. But we're going to do a lot of redox stuff in Unit 12. So we've got time, electrochem. It's fun. You'll enjoy electrochem, some of it. It's like how batteries work chemically and stuff. What we are going to focus on today, though, since we're just looking at reactions, is how redox scientists remove components of reactions to just focus on which items moved the electrons around. Let me say that again. The reactions that we're going to analyze in a moment are missing stuff. The reason they're missing stuff is because the scientist that was handling them was looking at it from a redox perspective. They only wanted to look at the species that moved electrons around, so they got rid of the stuff that wasn't a part of that. Our job is to figure out how to reincorporate the stuff they took out so that the reaction makes sense again. The steps to do it are long. Now, I paraphrased the steps over here. I'm hoping that you copied down the steps from your notes that were lengthier. That's good to have. I'm going to read off this. It's the same stuff, but paraphrased. But you'll want those steps in front of you. The bummer news about this is that I can't give you the steps on the exam. And I need you to realize that's never me being mean. My job is to always just give you whatever College Board gives you on the AP exam, right? I'd be doing you a disservice to give you stuff that they're not going to give you. So, yeah, you've got to know this. I don't think you have to memorize it, though. You just need to learn it. Those are two very different things. All right, so as you practice on Canvas and get good at half reactions, it needs to become a flow of, yeah, I have to do this next to get to that final answer. All right, so there's the steps that you copied. All right, I will be ultimately going off that, just my paraphrased version here. Because it's the basic solution step. Again, these aren't numbered. These numbered steps are not really applicable anyway in regards to the numbers themselves. All right, y'all, we're going to do two half reactions. Take a look at the screen. We'll do the top one first. Hey, do you see how it says acidic solution? That's important. Take note of that. Y'all, there's something seriously wrong with that reaction, though. Do you see the hydrogen on the left? Do you see the hydrogen on the left? Do you see the hydrogen on the left? Where do you see any hydrogens on the right? That's impossible, right? Law of conservation of matter says you got to have the same amount of stuff on both sides. But there's stuff missing. It's because the redox scientists got rid of it because they're just focused on the stuff that you see. We are going to discover the stuff they took away. Step one. Split the reaction by common. Here's what that means. See the MnO4? I need to build my first half reaction by taking one of the reactants and connecting it to whichever product it's got the most in common with. Of those two products, which one do you think the MnO4 minus has the most in common with? The Mn or the CO2? The Mn. Y'all, this first step is not supposed to be tricky. It's really, really obvious where the connection is. It's connected to the Mn plus 2. And if you ever can't figure it out with the first one, then go to the other reactant, because the other reactant will have more in common with the other product. And you can really see it if you look. The other reactant is H2C2O4, is H2C2O4. Do you see how that clearly has more in common with the product of CO2? We've done step one. We've split the reaction into two half reactions by connecting a reactant to a product and a reactant to the other product. We all right? See, this is easy. Now, step two, add coefficients if it helps you fix problems. I put maybe because you skip this step more than any of the other steps. Like, look here. How many manganeses are there above my finger? How many manganeses are there above my finger? Still one. I heard someone say two. I didn't ask what his charge was. I said, how many are there? There is one. All right? The manganeses are balanced. Now, we have oxygen issues, but not any that a coefficient will solve. Like, making more of those won't fix the oxygen. So, we don't need to add coefficients in the top half reaction because adding coefficients there or there doesn't solve any problems. But look at the other half reaction. Will a coefficient help us with any of the stuff? Yeah, it will. If you add a 2 right there, it actually gets us fixed in a couple ways, right? Now there's 2 carbons. Now there's 4 oxygens. So you just have to kind of feel it out. Now I'm going to do steps 3 through 6 all on the top, and then we'll rewind and do it all on the bottom. It's a better way to teach it. So the half reactions are going to be analyzed individually at this point. So we're up here and we're on step 3. Fix the oxygens by adding water. You can see our oxygen issue. Which side do we need oxygens on? The product side. Hey, how many oxygens do we need? So if we're going to fix those by adding water, how many water should we add? 4. Why 4? Because I need there to be 4 oxygens, and looky, looky, looky. Now there's 4 oxygens. We've done it. All right. Step 4. My bad. Step 4. Sometimes. I don't know. If there is, you fix it. If there's not, you don't. Step 4. Fix the hydrogens by adding H+. All right? So we're still, remember, we're only doing the top right now. Hey, which side of the reaction has a hydrogen issue? The left. Yeah, we don't have any over here. How many do I need to balance the reaction? 8. Yeah, look, 4 times 2 is 8. So I'm going to add 8 hydrogen ions over here. And that will balance the H+. Yeah. In a very systematic way, though. We all right? It's new, but it's okay. Step 5. Fix the charge. This one's a little weird. We've never really messed with this, but in a balanced reaction, the charge of both sides has to be the same also. And for us, for any time you've done chemistry with me or Lassiter, it's always automatically happened. But in half reactions, it doesn't. See how there's 8 pluses on the left and 1 minus on the left? Integer-wise, what's the total charge on the left? Positive 7. Very good. Now, I'm writing plus 7 up there, not because I need to, but just so you can see it. That is not a part of the chemistry. But plus 7, 8 pluses, 1 minus is positive 7, yeah? We'll ask a more specific question. So I'm looking at the entities. This entity is made up of 8 pluses. This entity is made up of 1 minus. 1 minus 8 pluses. I'm not doing anything yet. I'm analyzing what's there. I'll fix it in a moment. All right. Over here, anybody want to guess? What's the total charge on the right? Plus 2. Because there's 1 plus 2 and there's 4 neutrals, right? There's no charge on water. So now I've got Now I've got the charge on the left and on the right. They have to be the same. In order to fix it, I'm going to add electrons. Now, keep in mind that adding electrons is a negative experience. If I add electrons to one side, it's going to bring down the charge. So to fix them, I'm always making one charge drop to whatever the other side is. So where should I add the electrons, left or right? To the left. How many? 5. Very good, y'all. Very good. I'm going to add 5 electrons over here because if I make that number drop 5 times, it becomes that number. We all right? Sweet. And we have gotten through step 5 on one of the half reactions. Let's go to our friend down here. And let's rewind back up to step 2. Now, I already did step 2 because I was teaching. I added a coefficient because it helped us. But let's go to step 3. Fix the oxygens. What's our oxygen issue right now? None. We don't have an oxygen issue. Look, 4 oxygens. 4 oxygens. So y'all, while you go through this and you get good at it, realize that you're just kind of feeling out the reaction. If it's not broken, you don't have to fix it. Our oxygens are already balanced. Step 4, fix the hydrogens. Do we have a hydrogen issue? Yes. In order to fix the hydrogens, we always add a hydrogen ion. So how many should I add and where? Not 1, 2 to the product side. Now there are 2 H's on each side. Yeah? Now remember, we're not doing diatomic stuff because it's an ion. Ions don't follow diatomic rules. All right, step 5, fix the charge. Let's see if we're good at this. Somebody yell out, what's the charge to the left? It's 0. All right, the charges aren't hiding from you. If there's not a plus or minus being drawn, then it's neutral. Hey, class, what's the total charge of the product side? +2. Now, careful, some of y'all are just going too quickly. Look, 2 neutrals, 2 pluses, +2.
So if there's a coefficient, that's the charge that.
I mean, the coefficient multiplies times. There's 2 H pluses, so it's H plus twice for a total of 2 pluses. Yeah, the coefficient always plays an important role. Now remember, to fix this, we add electrons. Which side gets the electrons? The right. How many? 2. Because if you add 2 negatives over there, that will drop 2 times and match that. We're having fun. Are you having fun? All right, we have gotten through step 5 on both half reactions. Now we get to start to consider both of them again. Look at step 6. Equalize the electrons. This is a weird step, but here's the thing. The number of electrons in each half reaction have to match each other, and they rarely do at this point. Look, listen to what I said again. You see those 5 and you see those 2? That can't happen. They have to be the same number. And if they're not, which they're usually not right this moment, you fix it by multiplying the entire reaction. Sometimes just one of them, or in this case, we'll have to multiply them both. Here's what I'm thinking. That number and that number need to be the same. What is the lowest? I can't make a 2 become a 5, right? 2 times nothing equals 5 using whole numbers. So, what is the smallest common multiple, lowest common multiple of 5 and 2? We need them to both become 10. So what do? Well, watch. See this top reaction? I'm going to multiply it by 2. And it's just all the coefficients. It's the mole ratio. If I multiply the whole reaction by 2, this becomes 10, and this becomes 16, and this becomes 2, and 2, and 8. Do you see how I got to those numbers?
Charge 0.
No, the charge on the bottom is not 0, though. The charge on the bottom is 2. The electron. So, what do I need to multiply the bottom reaction to if 10 is our target? Yeah, let's multiply the whole bottom one by 5. And again, it's the mole ratio. So this will become a 5. This will become a 10, 10, 10. And the red numbers are the active coefficients right now. And that is step 6. We're so close. Step 7. Recombine the reactions into a single reaction. And then we're about done. Now, here's the thing though. When you're recombining the 2 half reactions, any items from the top reaction and the bottom reaction that match each other cancel out. It feels that way, but no. That's not what's actually happening here. Hey, how many electrons are there right there? How many electrons are there right there? They're going to cancel out then. 10 and 10, it's a perfect cancellation. So, these 10 electrons go away, and these 10 electrons go away. Y'all, that's going to always happen. At this point in time, the electrons on the 2 half reactions are going to be exactly the same. We made sure of it, right? We went out of our way. So the electrons will always cancel out. Do you see anything else that will? The hydrogens. Look at the hydrogens. Do you see how there's H plus in both? So here's how this works, all right? If I had 100 of one thing on one side and I had 80 of it on the other side, the 80 on one side would totally disappear and 80 of the 100 would disappear, leaving some over here, but they cancel out on a 1-to-1 basis. So, look at my numbers. I've got 16 here and I've got 10 there. So the 10, they're gone. And 10 of the 16 are also gone, leaving how many? 6. There it is. So here's our new active number. Up here, it's 6. And down here, it's none. It's all right. We're being patient with our brains. We're not looking at Cummings with that face that some of you are using. Y'all, there are no other items that match, and now we're ready to finish the problem by bringing down all of the remaining reactants, yielding all of the remaining products, and we are done. So here's what that looks like. So I'm looking for reactants. It looks like there are 6 H pluses and 2 MnO4s, permanganates. All of the reactants, 5 oxalics here. Now we'll switch over to the products. 2 manganeses. Whoa. 8 waters. And 10 CO2s. And we're done. Feel good about life right now?
Wait, what you put in the bottom?
I ran out of space. I put the 10 carbon dioxides. Yeah, y'all, this right here, it's not loco. All right, it's 10 CO2s. 10 CO2s. The purple is the answer. Now, remember how at the beginning we pointed out that it was acidic? It says acidic solution on the screen. That's why we get to stop. If it were basic, there would be one more step down there. Looks like fun. So you know what we should do? Let's do a basic one. Any questions before we get better at this on a new example? I'm gonna put Aspen out there, but that's I only have 9 minutes. Okay. All right. You'll be surprised how much faster this one goes now that you've seen the steps. So here we go. New example. Step 1, split the reaction. So I see BrO3 minus. Which product does it have the most in common with? Yep, Br negative. Very obviously. The other half reaction is going to start with Fe plus 2. And it clearly has stuff in common with Fe plus 3. Are you all right so far? All right. Let's just do the top first. Add coefficients. Should we? No. 1Br, 1Br. Coefficient won't help us. Fix the Fix the oxygens. Hey, what do we add to fix oxygens? Water. So there's oxygen over here. I need there to be oxygens over here. And I'm going to do 3 waters because I need 3 oxygens. Fix the hydrogens. I've got 6 over here. I need there to be the same number over here. And we use hydrogen ion to do it. Fix the charge. Can you find the charge? Y'all, we had some struggles with this. Hey, y'all, what's the total charge on the left? 5. Because there are 6 pluses and 1 minus. Integers. What's the total charge on the right? -1. Because look, there is 1 negative and 3 neutrals. Neutrals do nothing. So then what's the magical electron number to fix it? Yeah, 6. If you add 6 electrons over here, it'll drop the positive 5 6 times down to -1. Yeah? All right. Let's go down to the other reaction. We did everything we can do to the top so far. Let's rewind. Add coefficients. No, it's 1 to 1. We don't need to. Fix the oxygens. Do I need to fix the oxygens? No, there's no oxygen. Like, it's good. 0 and 0 is balanced oxygens. Do I need to fix the hydrogens? No, there's no hydrogens. This is good news. But I do need to fix the charge. All right. So charge-wise, it's pretty obvious, but you should see a +2 here and a +3 here. So what do I do to fix it? To the right. Add 1 electron. Because by adding 1 electron over there, that will drop 1 digit to that. All right, we're doing good. We're doing good. Let's equalize the electrons. Now we're looking at both reactions again, both half reactions. Hey, remember last time we had to multiply both reactions? Not this time. We'll only have to multiply one of them because remember, the electron counts have to be the same in both half reaction. What's the fix? Yep, times 6 right here. If I multiply the bottom reaction by 6, I will get 6, 6, 6, Ignore the bleeding walls. But now the electrons match each other. Ask questions if you have them. All right. Here we go. Rejoin the reactions. Remember, this is the moment where they rejoin, but things can cancel out. We know, hey, what automatically cancels out every time? Yeah, the electron numbers will always be the same. What else is going to cancel out? Nothing, because you're comparing the two half reactions together. There's nothing else to do. So let's write the reaction. All right, let's bring it down. I'm sorry? No, I mean, as long as they're on the correct side. So reactants first, which is going to be 6H pluses, a bromate, and 6 iron 2s, yielding products now, bromide, 3 waters, and 6 iron 3s. On the last question, this was the answer. I'm getting pushed up against the clock, but stay focused in. If this was an acidic solution again, we would be done. But it's not. It's basic. And you know what's true about basic? You're going to hate this. I'm sorry. But everything I'm about to say, you already wrote it down in your slides. But if it's basic, we add OH minus. Watch and absorb. Here we go. See that hydrogen ion? That's acidic. H plus, you might remember from last year, is an acidic substance. We need OH minus if it's basic like the problem says. Do you know what I'm going to do? I'm going to get rid of the H pluses by canceling them out with OH minus. So if I have 6 H pluses, I'm going to add 6 OH minuses to it. And that'll get rid of the acidity. But whatever I do to one side, I have to do it to the other. So I need to add 6 OH minuses over here as well. I'm not doing any L, just another plus. I'm out of space. This would be totally linear if I had more whiteboard space. Now, keep watching though, because this is awful. If you add H plus and OH minus, the reason it's no longer acidic is because it becomes water. So this is really, another way to write it is it's really 6 waters over here. All right, so instead of writing that, I could write that to represent that, which is important because this water was actually always there. We didn't know it, but in this earlier step, the water was there, which means it should have canceled out with that water. Hey, if I have 3 waters on one side and 6 on the other, the 3 will go completely away, and the 6 will drop to what?
3.
To 3. We would have used up 3 of them. So that means this number, it means, I'm trying to do my colors before the bell rings on me. That means that all of those will disappear, and 3 of those will disappear. And now we have a basic solution, and we're ready for a final answer. Let me show you. Here's the final answer to the whole question. It'll be 3 waters, doing the reactants. 3 waters, bromate, 6 iron 2s. Over to the products, Br minus. Here, I'm going to do the products right here. Br minus, 6 iron 3s, and 6 hydroxides. And it's those 6 hydroxides that make it beautifully basic. Oh, come on, Cummings, right?